host disabled, participant screen sharing. All right. Okay. Talking. Can you guys hear me and see my screen? Well, Paul, can you try talking? I'm not sure what my speakers are doing.
Check.
I can't.
Your speakers are fine. I can hear you.
Yeah, but I can't hear you. Means I wouldn't be able to hear a student. Let's see. Sorry, I had a Zoom meeting last night. I don't know if it did something. Yeah, I just can't hear you.
If you go into mute or unmute,
Yep.
up arrow, and you can select a speaker. So
Yep.
you can set the speakers to be.
Okay.
See if it works.
Yep.
Okay, hold on.
Check.
Yep, I'm good. Okay.
I'm gonna keep mine muted.
Yeah, that's probably a good idea. And probably you guys too. There'll be some feedback. All right, sorry everyone, technology stuff. All righty. So I think we made it most of the way through the distribution protection last time. I think we made it to sequence coordination. So I guess the plan today is make it through the distribution protection portion of the lecture, and then a little bit of a lab portion. I wasn't sure if I was going to be able to have it completely pulled together, just because I had a couple things going on last week, but I was able to. So Paul should have sent you guys or uploaded to Brightspace a logic diagram that we'll work through today. It's pretty similar to the one that we worked through towards the beginning of the class, but there's I made some additions to it so that it would have automatic reclosing. So we'll work through that. Okay, so I think we left off. We were talking about the fuse saving schemes. A quick recap image of that is what we see on the picture here to the right. The way that would work, just as a reminder, is your first trip and second trip in this particular example would work on that curve 3. What's typically called a fast curve. And then trips 3 and 4 would operate on that curve 2, which typically be called the slope curve. Goals for fast curves to save the fuse, and then the slope curves to give the fuse an opportunity to coordinate with the relay. Once we've kind of established it's not a temporary fault. So figured I'd go back over that. It kind of plays into the sequence coordination. So sequence coordination. Let's say we were setting relay 1 on the right. So we would want to coordinate with and have a fuse saving scheme with fuse 1 that's feeding its own load. And we would want to coordinate with recloser 1. Now, recloser 1, let's say it's existing and it's already got a fuse saving scheme in place for fuses 2 and 3. So let's see. So we're going to choose the settings that we have on the right here to coordinate with and have a fuse saving scheme with fuse 1. So imagine the settings that we've picked. We're going to have a fast curve that will, from relay 1, we've got a fast curve that will save fuse 1. And then we've got slow curves that will allow us to coordinate with fuse 1, or else if there was a trip out on the fuse 1 load, we would lose everything that fuse 1 is beating, but we'd also lose everything off of that recloser. And then also we want to coordinate with that recloser 1. We don't see the recloser on here, just the fuse, but oh, here it is. Okay, I did it in two sections. So that's our relay coordinating with the fuse. We can see we have the fuse saving and then the tripping. And then you can see here that recloser has its own set of fast curves and slow curves that will coordinate with its respective fuses 2 and 3. So we have 2 sets of curves shown there. So we chose our settings to coordinate with the fuse. Now we're checking them against the recloser. It looks like this works. We're gonna save fuse 1 and then, trip once we get to our slow curves. And then here, the downstream recloser fast curves will operate before our fast curve. You can see that 3F is going to operate before 1, and then its slow curve is going to operate before our slow curve. 3 is going to operate before 2. So the recloser fast and slow curves do operate faster than the relay fast and slow curves, so coordination is achieved. Yep, I just said that. As the recloser cycles through its reclosing sequence, it will move to its slow curve. The relay has not tripped because it coordinated with the recloser. The relay remains on its fast curve. So the challenge that we're going to see here is imagine we had a fault right. Can I get my mouse? Imagine we had a fault right where my mouse is. Well, what's going to happen is recloser 1 is going to trip and it's going to reclose. It's going to trip and it's going to reclose. So it's gone through its fast curve and it's gone through its fast curve. Now it's going to go to its slow curve. But our relay never tripped because it was coordinating with recloser 1. Well, now because recloser 1 has gone through its fast curve, and it's on its slow curve, we never tripped. We're on our fast curve. So now our fast curve will trip faster than their slow curve. And in that case, relay 1 will operate and we will inadvertently lose our load that's off of fuse 1. So kind of trying to explain it rather than read right off the slides. So the problem, that's the problem. So to prevent this, we're going to tell the relay to skip shots whenever the relay has detected something that it can qualify as a fault. Likely, our pickup going. So yeah, I'm not going to get into the logic of it because it's actually on a logic diagram. Sequence coordination is pretty involved and requires some knowledge, of the relay word bits that takes a little bit of reading in the instruction manual. That's the basis behind the sequence coordination, is making sure that our relay will skip shots whenever our downstream recloser trips and we pick up, so that we can stay in line with the recloser as it goes through its reclosing sequence. So that was sequence coordination. Step is distributed generation. We do have some rotating machine-based distributed generation in Maine. We have a lot of smaller hydros that tie into various distribution circuits. I know personally I've had some opportunity to be on a few biomass sites that were tied into distributed generation, that are rotating machines. But solar PV inverter-based generation is becoming super popular. I'm sure you guys can all see it just driving down the road. It's impacting our lives. It's creating a lot of work for us. It's it's a real thing right now. And as I said, the rotating machines are still out there. And by rotating machines, I mean synchronous generators or induction generators. They're out there, but they're becoming the minority. These things are going in everywhere. I think Maine, for example, I think right now has got about 300 applications in for these distribution type PV sites to go in. So yeah, there's a lot of them. Another big thing that's going along with that, they kind of have to go hand in hand at times, is battery storage. Battery storage helps fix challenges with peak generation, not lining up with peak demand times. So you got to think, noon, you're going to have your peak generation with a solar PV, type of generation. And I think 6 o'clock, 5 to 6 o'clock is typically considered the peak demand time. Everybody gets home from work. Everyone turns on the stove. They might turn on the dryer. I think if you were to look at a curve, a load curve, 6 o'clock is usually the peak. So battery storage, they charge all day. They discharge when it's not sunny or windy or, whatever type of generation we don't have control over. So these sites tend to be under 10 MVA for the distributed generation. Larger than 10 MVA requires more stringent regulations. I think they actually have to report to ISO. They get bigger than 10 MVA. So it's a pretty solid line. You're going to see everything stay under that 10 MVA for the most parts. And then typically if something's larger than 10 MVA, a lot of times you'd see that get tied into a transmission system. And then in Maine, these sites are owned by independent investors or independent power producers and not the utility. That's a pretty solid rule in the state of Maine. I think they had something called deregulation maybe 10 to 15 years ago where that actually became law. The power delivery company could not own the generation. So that's still a thing here in Maine, but it's not the case in other states. I know California, the power delivery company can own the power generation. I think the same thing in New York. One definition, penetration level. That is the rated power output of the distributed generation over the peak load. So for an example of that, we had 1 MVA of distributed generation on a distribution line with a peak loading of 10%. The penetration level is 10%, or 10 MVA, the penetration level is 10%. We often don't see that penetration level get up over 100%. The intention isn't usually to backfeed off of the distribution system and up into the transmission system through the, what's meant to be a step down transformer. So usually that's not the goal. And then the generator step up transformers, GSUs, may or may not have a high side winding, which is significant because it adds an additional ground source on the distribution circuit. Inverters, You have your panels themselves, but a lot of times your inverters are kind of considered the generators, if you would. They have a lot of built-in algorithms. One of the big ones that they have is anti-islanding. That is, if the utility is lost, they'll turn themselves off in under 2 seconds. Whenever we go to a distribution circuit that has inverter-based generation, we kind of make that assumption. It's if a fault happens and we are able to trip off that distribution circuit, that inverter will shut itself off on its own within 2 seconds. But they're kind of finding that doesn't work as smooth as they like. Challenges can occur if multiple inverter manufacturers are on the same circuit. So these algorithms that will shut themselves off in 2 seconds are actually proprietary for those manufacturers. So it's difficult to know how they work, and they don't share how they work. So if you were to have 2 different manufacturers, they may not know how their anti-islanding systems work with each other, and it's difficult to guarantee that they'll actually interact, in an expected way. They may actually prevent themselves from, coming offline automatically. So that's becoming a pretty real consideration just with the magnitude of these distributed generation systems. So here's a pretty typical distributed generation arrangement. A fuse 3 that's hanging out, it should be deleted. So let's say we had a 12.5 kV substation bus with a breaker and a relay protecting that distribution circuit. This is pretty similar to the one that we had before. We've got a fuse feeding some load. We've got a recloser feeding 2 more fuses that are feeding some load. And let's say they were going to tie let's say it's a solar generation site into this distribution circuit. Would be right here. There'd be definitely a line of demarcation between what the utility owns and what the generation owner owns, or the independent power producer. This is a pretty typical setup here. Think of that as where you have your inverter. You'd have your panels tie into the inverter. It would convert it to AC, probably at a voltage like 480 or maybe 600 volts. And then this generation step-up transformer would step that up to the 12.5 kV. It would probably just have a fuse protecting itself, and then utility would usually have their own additional recloser on the utility side. Oh, what did I do there? So inverter fault characteristics. This is a challenging one. We've become so familiar with the fault characteristics of a rotating machine. An experienced protection engineer kind of knows them inside out. But the rules change with inverter fault characteristics, and I know it's been a little bit of a learning curve for a lot of people. And when these were starting to become popular, it was a pretty major concern for for a lot of protection engineers and how this was all going to work. The big reason for the difference in the fault characteristics is inverters don't have inertia or stored energy. We think with a rotating machine, that shaft with the prime mover behind it, it can't just stop. It's got to keep moving and slowly, slow down. That's not the case with an inverter. An inverter just shut itself off. So there's a pretty big difference in that inertia is the primary reason why. Different inverter manufacturers may have different fault characteristics. You can usually look them up on their data sheet. So the information I below might be typical, but may not represent all cases. So a big one, many inverters do not source zero sequence current. That's not a huge deal because we can put a ground source in to make up for that. Either a zigzag transformer or a delta Y transformer. So like here, for example, this inverter based generation would not be able to source any zero sequence current out onto the system. But if we were to make this a delta 600 volt side and a Y grounded 12.5 kV side, it would be able to source zero sequence current out through that neutral of that transformer. So as far as what goes out onto the system, the fact that it can't produce a zero sequence current, it's not that big of a deal. We got a way around that. The one that's becoming a much bigger deal, the fact that they also can't source a negative sequence current. Putting a ground source out on that distribution circuit is not going to help with that problem. Maybe a quick chance for someone to maybe know the answer to this. I think we talked about it in that first lecture there. Why might a negative sequence source be important? Yeah, forcing you to go pretty far back into the memory banks on that one. But the big reason is for the overwhelming majority of our directional elements that we set, they're actually based on a negative sequence polarized impedance. So that means if we don't have adequate negative sequence current, we're not going to have an adequate negative sequence impedance for us to tell if faults are forward or reverse. And some directional elements look at both negative sequence and zero sequence, but there's a lot out there that are only based on that negative sequence element due to the concerns of mutual coupling interfering with the zero sequence, creating some false operations. So that's one myself. It's not a big deal. Maybe right here on the system, but I am curious to see how, as these inverter-based generation sites really start to outweigh, the rotating machine-based generation sites, how that's going to affect the transmission system, where most transmission, directional relays may not start to work the way that they had been originally designed. So that'll probably be something will be a serious challenge. If any of you guys become protection engineers, we'll be up against. But anyways, so yeah, can't source the negative sequence current, and then many inverters do not have a high ratio of fault current magnitude to the load rating in comparison to a rotating machine. So by that I mean, let's say I were to have a solar inverter-based generation site that was rated for 1 MVA. A typical short circuit, capability of that inverter site might be 2.5 MVA. That's a ratio of 2.5 would be pretty typical. it's tougher to distinguish that fault current from that load current. Someone jumping in? Does someone have a question, or is it just accidentally hit the mute button? Okay. So it's tougher to detect that difference between fault current and load current than than maybe a more typical ratio of maybe 8 times the fault current that you might see with a rotating machine. Just in general, out of those 3 bullet points, the challenge that I'm talking through is it's more difficult to distinguish between faults and load currents with these inverter-based generation sources, and even to distinguish things like directionality. So there's some challenges associated with that. Okay. Utility considerations. So how does this impact our existing design? We already talked about one example of relaying in the directional elements. But very oftentimes a system impact study needs to be performed, and these applications need to be reviewed pretty thoroughly to make sure that they're not inadvertently pushing any of the equipment on the system past their limitations. So one consideration is that the total fault current of the system has been increased. So now let's say we had a breaker that could interrupt, let's say 10,000 amps, and we introduced another 1,000 amps. We need to make sure that it can still interrupt that. Our 50 elements that used to be set based on a system strength behind us, well, now there's more of a strong source behind it. We need to reevaluate those to make sure that they don't overreach, whatever it is that they're intending to not overreach, usually downstream reclosing. If the GSU has a ground source, the 3 I0 currents may be reduced in certain branches depending on the fault location, even though the total fault current has increased. And by that, I mean, let's say this was a ground source right here, a Y grounded winding. Let's say we had a ground source over here. So if we were to have a fault, let's say right here, the total fault current would increase because it's being sourced from, the 2 different ground sources. But that actually often makes up a current divider, where a certain percentage of the ground fault current will flow through this branch of the 0 sequence network, and another percentage will flow through this branch of the 0 sequence network. And very often this ground source here, although it increases the total fault current, will reduce the fault current through this branch. So we would need to make sure that this relay has adequate sensitivity to still be able to reach and protect the entire line. Another consideration, line voltage regulators and load tap changers may need to be adjusted if line drop compensation is used, or if backflowing is possible. So essentially just thinking of those generation sites holding the voltage up, it affects the other voltage regulation on those distribution circuits. Now fault current can flow in both directions, where it may have previously been a radial line and we hadn't been using directionality. Now we may need to use directionality. if reclosing has open intervals of less than 2 seconds, or even if, we can't depend on that anti-islanding, we may need to put a sync check element in for the closing of that circuit breaker. And then it should be checked to see if distributed generation already exists on the distribution line and if similar manufacturers are used. If we do see that, that may be a concern, that we can't rely on the anti-islanding. We've got some other options that may need to be investigated. A pretty common one is putting ground over voltage or 3V0 protection on the line. And then, because one consideration is a ground fault on an ungrounded system will have a voltage rise. That's pretty well characterized by a 3V0. And then even the possibility of using some direct transfer tripping maybe needed as well. If that anti-islanding isn't reliable. So I think that's it for the lecture. I did want to put some references on here. Just as a reminder, you all have access to the IEEE library through Fogler Library. Take as much as you humanly possibly can before you graduate. Take it all. Really great stuff. They cost money when you do graduate. And then I had a few books on here. You may or may not be able to find these on the internet, but there's some really great resources, pretty well known in industry. And then again, SCL.com has a lot of great information. Their instruction manuals that teach you how to use their relays are really great at teaching you how to use their relays, but they can really teach you a lot about fundamentals, behind those relays. And then they have a lot of application guides that are really great. Yeah, that was that. We took about half an hour, so that wasn't too bad. I guess before we transition into a lab portion, does anyone have any questions about what we went over, the distributed generation or sequence coordination, or maybe your homework? Going once, going twice. All right. All right, we can make a transition now. I apologize, it was pretty last minute. I had some stuff going on last week, so I wasn't 100% sure if I was going to be able to get it put together, but I'm glad we did, because lab portions are always a little bit more fun. I prepared some relay settings for one of the 421s in the lab. If you guys remember, it's going over, the relay at the beginning of the class. It's the same basic setup. I've just added a few things to it. The primary thing that I added was this sheet here for reclosing. I think before the relay just had manual closing. Now we've set it up for automatic reclosing in addition. You all should have this logic diagram. As I move away from this logic diagram and open up the HMI interface through Accelerator, you should be able to follow along as well. I've got a printed off version here that I'll be playing around with. To briefly go over the logic that we put in here, got a push button. This push button will turn reclosing functionality on or off. Maybe in some maintenance situations, you don't want reclosing. You can turn it off, so it's not going to work. Another thing that drives that is we have a tagged hold condition that prevents the breaker from operating on or off under any situation. It's generally a maintenance condition, but more specifically part of a tagging procedure for technician safety. If they put this relay into hold, it will prevent us from turning reclosing on and automatically drive us into reclosing off. Some other things to keep in mind here. Our trip is what's going to drive our 3-phase reclose initiate work bit. So if we trip, that's when it will do its reclose initiate. We have our 79 drive to lockout. So if we found out that this trip was from a breaker failure condition, it's going to drive our reclosing straight to lockout. We're not going to use any skip shots like we might if we were going to do sequence coordination like we talked about earlier. 79 BRCT, can't remember that one off the top of my head. This is our manual close right here. It's going to work exactly the same as before, where we have a push button or a control switch. We have our 3-phase close provision. We're just going to keep that as a 1. Oftentimes we might use things like a sync check or a live bus deadline to supervise our reclosing, but not drive it to lockout. And then our close word bit is going to have an internal latch, and then it will unlatch itself when that breaker actually closes, or if there's a trip, kind of so that it can be reclosed, if you would. Yeah, we'll walk through this logic, and I've got accelerator open. This screen right here is somewhat accurate. The labels on the push buttons are correct, so those will match what I've got configured on the relay itself. So where we see the first one being 52 control switch control enabled, that's accurate. All 8 of those are accurate. The lights are accurate. You can see right now we have breaker closed. That matches what you will see if you're looking at the front of the relay. And then over on the left, these ones, unfortunately, accelerator won't let you change the labels on these, but the colors will actually be accurate. Like if we go to the logic diagram, we can see that LED 8 would be a 79, which is the ANSI number for reclosing lockout. If we were to have a 79 lockout, our push button 8 would actually light up on the screen, even though unfortunately it won't let me change it to say closing lockout. Sorry. It's a little tricky remotely, but I'm going to try my best. You guys will see this. I'll continue to talk. Try to kind of collectively follow the lights on this screen, but also that logic diagram that we have as I talk through it. So. Okay, so we will start with testing the 79 on-off function. Right now, 79 is on. I'm going to turn 79 off.
It's really hard to hear you.
Oh, okay. Sorry about that. Okay, so we turned 79 off. We turned 79 back on. Okay. I'm going to turn breaker hold on. We can see that drove us straight to 79 off. I'm going to try and turn 79 back on. Okay, it won't let me. That's because we're still on hold. We'll turn that off. And now I'll turn it back on. You guys will see the 79, the LED 8 is on for 79 lockout. That's because I had reclosing off. That'll reset itself after a period of time with the breaker close. See that here in a second. But all right, so now to simulate the reclosing sequence, we're going to turn test mode on. Test mode will be on sheet 1. Turn test mode on by hitting PB4. Okay, so we can see test mode is on. That LED is flashing in front of me. With test mode on, now what I can do is go over to my test trip. You see test trip, I believe, on sheet 4. So to walk through, I'm going to walk through this whole sequence, and then we will do it ourselves. I kind of got to walk through it ahead of time to make sure that, you know, I've only got so much time with my open interval, so I can't really talk as much while it's going on. So we're going to press push button 3. Push button 3 is going to be a test trip. If we follow that through, that'll go to sheet 2. The test trip will go through on sheet 2. It'll hit the trip equation. Once the trip is issued, that will go on to that rat hole on sheet 3 for reclosing. We follow that. We can see that trip hit the reclose initiate. So when it hits that reclose initiate, it's going to wait for that first open interval. We can see down in the bottom left that that first that first open interval is 5 seconds. So it will automatically reclose in 5 seconds. Once it recloses, I'm going to do another test trip. And then, you know, it'll work its way through its reclosing cycle. So what we're going to expect to see is a test trip, and then 5-second open interval, a reclose. I'll then do another test trip to a 10-second open interval. It'll reclose, do another test trip, go through a 15-second open interval. It'll reclose, and then I'll do a last test trip, and then it will drive itself to lockout. Because it's tried as many times as it can, and it's determined that it's a permanent fault. So I'm going to push button 3 and give it a test trip. So we can see now breaker is open. It just closed. Give it a test trip. Now we'll go through the 10-second open interval. Test trip again. 15. Before I came in today, I had these actually at 15, 30, and 45, so they were a lot longer. Feels like forever. And then last one, we tripped and we drove to lockout. We can no longer go through the reclosing cycle. So that's a full sequence. If I would have not given it a test trip maybe after 2 cycles, it would have just, you know, kept on going. It would have restored the line automatically, and things would have been great. So that's working through the test cycle. I'll look at that. This will remain in lockout until the breaker has been closed and stayed successfully closed for a period of time. Yeah, so that lockout will automatically reset itself. The breaker's been closed for a period of time. So now, why don't we try the breaker failure version of this? So let's say we had a trip, but our breaker didn't trip, and we've indicated that the breaker failed. So we can walk through that. The only difference between this and the last test is I've set the logic up to actually not trip the breaker. If that makes sense. So it'll be able to tell that the breaker has failed because I told it to not trip. And then we should see that it will drive itself straight to lockout and it will not reclose. So again, I'll put it in test mode. And then this time, rather than give it a test trip, I'm going to give it a test breaker failure trip. So we tripped. We can see the 79 lockout come in. We can also see that our DF trip, which would be our target 7, came in. So yeah, we're not reclosing. Let me close this back in. Okay. So another one that we'll try is we'll try reclosing with reclosing off. Let's see. Yeah, hopefully it shouldn't reclose. I gotta wait for that LED to set itself. It's a setting called a reclaim time. I think you guys recently saw something called switch on default. It will actually automatically prevent itself from reclosing if there is a switch on default condition. Because the breaker has to be closed for a period of time for it to reset itself. It'll remain in 79 lockout until it's had that time to say, okay, we're closed, it didn't automatically trip out, we're good. So, okay. So now we can turn reclosing off. You'll actually see the act of turning reclosing off will drive that 79 to lockout. But you know that you can't reclose. But just fun, we'll try a test trip and see what happens. So we tripped, and yeah, this one we're not reclosing. So some other things to keep in mind. We are only going to reclose for that trip. If we look on sheet 2, that's really meant to simulate a line protection trip. We've got our overcurrent elements and distance elements that are intending to be looking out onto the line. Now we can actually test it's not going to reclose if we do a manual trip. So I can come here, turn test mode off, reset everything. I'll turn 79 on. Close the breaker. We'll give that reclose time 2 seconds to reset itself automatically. I think it's like a 20-second. Sorry. Okay, so that reset itself. So now what we're going to do is we're going to do a manual trip. With our manual trip, we did not reclose. And then I talked about the switch on default. We can walk our way through how that might work. So let's say the breaker has been open for a long period of time. Someone's going to come through, and rather than it being a a reclose, they're just going to do their manual close. So they come through, they do a manual close. Oh, we immediately trip out. Okay, no reclose. And I think Paul and I were talking about the switch on default. That was a good example of a situation where we wouldn't want to reclose, where they have those safety grounds out on the line. And there's likely people, in the station. So figured we walk through that it will actually prevent the reclosing in that situation. So I think that's all I had. I probably ran through it faster than I intended. Yeah, I hope not being able to see the relay didn't make things too tough. I'm hoping being able to see the LCD screen there, even though the labels on the left were inaccurate, was able to help out. I guess does anyone have any questions on that or what we ran through? Oh. Yeah, still got a little bit of time. So, okay. All right, well, if we don't have any questions on that, I can click out of here. Yeah, I'll pull them after. So I guess I can use a little bit of spare time. We can run through some of those settings that we did configure. Let's see, where is it here? Trip. So we can see, this is where we configured things on that logic diagram, like our reclose, enable. We've got our unlatched trip. We have our reclaim timer equation. You can actually delay that reclaim time. We've got our manual close. That's the actual time that we're talking about with the reclaim time. Breaker one, supervision. It's just kind of how long are we going to let that supervision not be met before we drive to lockout. We had it set to 1, so obviously it's going to get met. But if we had a sync check, how long are we going to give it? Let's see, 3-pole line open failure. Yeah, I can't remember that one. We had our open intervals here. Again, they were 5, 10, and 15 seconds. I probably could have stuck with the 15, 30, and 45. We'd still be going through the logic. But yeah, I guess those are some of the basic settings and where you might set them for the reclosing. I guess last chance before I let you guys out early. Is there any questions on the homework? Now's your chance. I think it'll be due Tuesday, right? I believe.
Is that homework 7?
Let me double check. Yes, homework 7.
Yeah, could we take a few minutes and kind of do like the 40,000-foot view? I don't have a lot of experience with quickset yet and these curves, so just kind of getting off on the right foot would be a huge help.
Yeah, definitely. So first one's just more data collection, forcing you to steal information off the IEEE library, whether you want to or not, you're going to. So you're probably talking about these settings right here.
Yes, and then perhaps actually using the Excel sheets that you've supplied to kind of play around graphically.
Okay, yep. So these guys, just kind of quickly, I can't remember if I said this is going to be a 451 or a 421. 451, almost the same as a 421, which I have open here. So those, to navigate to find those, it's not super inherent, but we'll be working in group one, set one. The reason we're in group one is because we have chosen group one and all the other groups are disabled because they have zeros. So you go to group one, set one, and you find those settings further down on this list. Phase instantaneous, ground instantaneous, and then you've got your selectable inverse time. You do have to go to your relay configuration and enable those word bits. So I think in that situation, I had my 50s as off, but I could turn them on just like that. And now they're available. So pretty quick explanation. I think the instantaneous is relatively straightforward. You've got your pickup, you've got your time delay, probably just keep that at 0. And then a torque equation. This one just happens to be 1, which means it will always work, but you can put different things in there. And then the selectable is just the inverse time portion. So you can give it an operating quantity. This particular one has a 3I0, so a ground over current. Again, your pickup, your curve selection. Right now we have a U3 selected. You can see the relay has U1. The relay has U1 to U5 as options, but also C1 to C5. Your Excel spreadsheet is just going to have U1 to U5. Your time dial. Your time dial will actually move your curve up and down. It won't affect your pickup at all, but it'll move it up and down. And I guess another good visual is your pickup will move your curve to the right, but it will also move your curve up if you're trying to maneuver it. You got your electromechanical reset. That just has to do with if you were to do something, let's say like sequence coordination with a downstream electromechanical relay that has a rotating disc. That rotating disc takes time to rotate back to a 0 position. So it's just an option of, do you want to mimic that rotation and not have it reset instantly, or do you want it to reset instantly? Because a computer can do that. And then you have your torque equation. This one is actually directional. So this is a directional ground forward. So that's a quick overview of the settings themselves. The coordinator, open this guy. So any questions specifically on it?
Not yet. I've been trying to dive into the PDF, and I think it's more general understanding. If I get a foundation, then I might actually know what to ask next.
Alrighty, yeah, definitely. So I think the homework tells you what fuse you're gonna have.
Yeah.
Let's see here. What did we have?
It's 200K link fuse.
Okay, so we can come in here. Mine's already set to 200K, but you could change it to something else, but you want that to be 200K. It's gonna yell at you, but don't listen to it. I don't know what the fault magnitude was on the homework, but we'll just leave it at 6,000 amps for now. I tried to color code this to make things line up a little bit. This orange line is representative of the total clear time of the fuse. So I tried to have orange and orange. So this orange line is essentially the fuse. This blue line is our relay characteristic. I've got, blue line for the relay. And then this red box over here is our fault magnitude. Made that a red line. So as you adjust this fault magnitude, we're going to see that red line move over. So right now it's at 6,000 amps on the x-axis. I can move that to, let's say, 2,000. Okay, so we saw that move over to 2,000 amps. A nice feature of this is if we were to move a line over from that blue line on the y-axis, which is our time, our dependent variable, if you would, we can see that it operates in about 7 seconds. This box over here tells you that, pulls that number for you. And then we can see here the fuse total clear time is about 0.8 seconds. Again, we can see it pulls it. And then it just subtracts the 2 times here. So that time minus that time, we see that the fuse, my computer's getting mad about something. You can see the fuse is going to operate about 6 seconds faster than the relay. So we're not going to touch the fuse much because we already know it's a 200K. The homework should tell you what the fault magnitude will be. Really what we're going to be playing with is our relay settings here. So your homework should tell you what you want for a current transformer ratio. I don't know if it lines up with this or not, but right now we have 240. Our inverse time over current element is set to 3 amps secondary. We can also think of 3 times 240 will get us to 720 amps primary. It's not going to line up exactly on here. I think I cut that off at 1.25 multiples of pickup. So that you'll see this kind of start at 1.25 times that 720. And that's just because if you try and put a curve right on 1 multiple of pickup, it doesn't like it. Have a indeterminate number in that situation. So a factor like that is pretty typical. Our curve selection, I think I gave you a hint on which one to use in the homework. We're coordinating with a fuse. Right now I'm on something called very inverse, U3. U4, extremely inverse, often coordinates with fuses pretty well. You can see it actually just shifted shape a little bit, and it kind of fits the curve of that fuse a little bit better than the U3 did. Like I mentioned, your pickup, visually, as you increase that, it's going to take your inverse time curve. It'll push it to the right, but it'll also push it up a little bit. We can watch that. Boom, we saw that shift. That back to 3, went back. And then your time dial will move that curve up and down, but it will not shift it left to right. So let's say I change that to 6. Okay, we can see that went down. I could change that to 2. Okay, it went really far down. your instantaneous pickup. This is your pickup that you will operate at in this situation without delay, because we have the delay set to 0. So same thing, 20 times 240 is 4,800. It's a lot of fault current. So we will operate instantaneously. Maybe I wanted a delay to help coordinate. Now our 50 element does not operate instantaneously, but it operates in 10 cycles. We can kind of visually see that. And we could even more particularly see it here. So I just moved my fault into my instantaneous region. So we're now at 4,800 amps of a pickup, but we're seeing 6,000. So we're going to operate. You can see here, I'm set to 10 cycles. So my relay operated in 0.167 seconds. Little conversion there. I could bump that to 0. And now I operate instantaneously. But the basic goal of the homework is going to be evaluating the relay settings and the fuse at a particular fault current, and making sure that you have a certain time difference between your relay and your fuse. So your homework will tell you the fault magnitude. Your homework will tell you what fuse you're using. It's really going to be you guys playing around with your relay settings to achieve a time difference that you are looking for, that the relay specified for you. Like I think one of the criteria was to make sure that your time difference was either 120 milliseconds or 130% of the total clear time, whichever is greater. You'd pull those numbers from this table here, and make sure that you're meeting that criteria, along with some other criteria that's set earlier in the assignment, such as what your acceptable pickups are and things like that. Yeah, the Excel spreadsheet, it's doing its very best to pretend to be Aspen. Aspen's a fantastic program. I know you guys went over it a lot with Andrew. It's also a very expensive program. I know, if you were a for-profit engineering firm, it's a lot easier to have it than a school that has funding. But like I said, hopefully this is pretty user friendly and kind of gives you a chance to play around with these shapes, because the way that these are changing and moving are exactly like Aspen. So hopefully it gives you a chance to put your hands on the driver wheel and get a good feel for it. Any additional questions on this spreadsheet?
I didn't have one on the spreadsheet, just on the homework in general. I assume here to use the relay coordinator for all of the questions involving downstream devices, and then only when you specify fuses to use the fuse coordinator.
Yes. Yep.
Okay. Thank you.
Yep. And if you have Aspen, you can use Aspen too. But yeah, exactly. You'd have to actually find a 200K fuse on Aspen. But yep. Hope that is the wrong Word document. Let's see. Yes.
So we're not just using these coordinators.
I think you really only have to use the fuse coordinator. I think most of the questions are kind of, figuring out what is your acceptable pickup criteria. But I think the homework assignment itself is actually a scenario of relay and fuse. I think you would only need to use that. Yep, exactly. Yep. But if your closest device was a relay, then you might use the other one. So yeah. Let's see. Yeah, so the homework, the questions really kind of lead into each other. I'll do my best if you make a mistake on question, 1, and it, perpetuates, as long as you still use the right methods from there on out, I'll follow it through. And, it's more about, using the right methods than, coming up with the right answer per se. So yeah, I think that's it.